In this video, we go back and look at derivatives as a rate of change. I also go over basic motion problems, which involve position, velocity, and the acceleration of an object moving along a straight line. Let's just start this with a little bit of review. So the instantaneous rate of change of a function with respect to x is just the derivative, which is the limit of the difference quotient, provided the limit exists, and we consider the domain to be the set of all values so that the limit does exist. Notice that this is essentially just the limit of the average rate of change. In fact, if y equals f of x, then for a given change of x, there has to be a change in y, and the limit of the ratio of the change in y over the change of x as the change of x goes to 0 is just the derivative dy dx. This nice notational connection between dy dx and the change in y or the change of x is kind of useful for rate of change problems. So let's just do an example. The area is related to its radius by the formula a is equal to pi r squared. So just how fast is the area changing with respect to its radius when the radius is 4 inches? So your first question probably is why should there be a derivative? Well, it's probably because this middle sentence right here, or at least part of it, because they're talking about changes. So there's a change in radius, and that correspondingly gives you a change in area. Since we're talking about how fast it happens, that's a ratio of those changes. So I need at least this. But they never gave me what the radius was changing from this to that. They gave me only one radius. That's an instantaneous rate of change. So I need to take the limit of that ratio as the change in radius goes to 0. And we all know that's just the derivative. So I know what a is as a function of r, so I just perform that derivative like always. That gives me the rate of change of the area with respect to radius. In particular, I want to know what happens when the radius is 4 inches. So just plugging it in, that gives me then that the rate of change is 8 pi squared inches per inch. Now you may wonder, why did I write squared inches per inch? Where do those units come from? Why don't you just cancel them and give me inches? Well, don't forget that this comes from a change in area on top and a change in radius on bottom. So in the denominator, I should have had inches units, and the numerator, I should have had squared inches units because it's an area. So our final answer goes like this. When the radius is 4 inches, the area is changing at a rate of 8 pi squared inches per inch you change the radius. That's it. Let's look at a typical rate of change kind of problem, motion along a line. So let's suppose that we represent an object's motion so that we know its position s on a line as a function of time t. So s just gives you the position of the object on the line at time t. Well, as the time varies, you can then talk about the displacement of that object as, say, the time changes from t to t plus the change of t. The symbol for displacement is just the change in s, and it's literally just the difference in the two positions, where you take the position at time t plus the change of t and subtract from it the position when the time is just t. Now, in my picture, I've drawn it so the displacement is positive. That doesn't have to happen. Displacement could be positive or negative. Also, don't get confused with displacement and distance. They're not the same thing. Think of it more like, if you want to know displacement, if you look at the object when time starts, but then close your eyes and let it move around, and then open your eyes, the only thing you'll notice is the beginning and the end. You don't care how it goes, it got there. So displacement is literally just the difference in the positions, ignoring the actual motion to get there. But if the object is always going, let's say, to the right, or always going, let's say, to the left, then displacement is almost distance. Distance then is the absolute value of that displacement. But that's only true if the object never ever changes direction on the line. So over this time period from t to t plus the change of t, we can compute the average velocity. It's just the overall displacement divided by the travel time. So it's the change of s over the change of t. Notice that's a difference quotient. So if I want to know the instantaneous velocity, all we do is take the limit of that as the change at t goes to 0. So symbolically, you can see then that velocity is nothing but the derivative of position with respect to time. Now, if you might want to know also the speed of the object. See, velocity could be either positive or negative because the displacement could be positive or negative. Well, then if you take the absolute value of the change of s, you get distance as long as you don't change directions. So it seems reasonable then to say that the speed is just the absolute value of the velocity. So let's explore that definition a little bit. Look at this graph. This is the velocity of a particle as it moves on a line. Now, this is not the position, it's the velocity. So let's just see what we can learn from it. If you look at the first portion of the graph, in this case where the portion is above the t-axis, that means the velocity is positive. Well, velocity, though, is a displacement per change in time. So if you have a positive change, you have to have a positive, then, displacement in order to get a positive velocity. Well, that means then the object is moving to the right in the entire time. If we assume to the right is positive and to the left is negative, like is traditional for number lines. In the next section, notice the velocity is negative. So for the same reasons, a positive change in time would have to correspond to a negative displacement. So therefore, the object is moving to the left in the entire time. In this time period, the velocity is 0, so then the object's not moving. And in the last section, we have that the object's velocity is positive, so the object must be moving to the right on the number line during that time period. Now let's take this graph and break it down into sections. Now, speed, if you remember, is just the absolute value of velocity. Absolute value can be thought of as distance to origin. So here in the graph, going up or down is not really speed. It's more going towards the t-axis or away from it. As you go towards the t-axis, you must be decreasing speed because you're decreasing the absolute value. If you, though, go away from the axis, you must be speeding up. Okay, so then this little section here, you're not going away from the axis at all. So then that's a constant speed. In this little portion, the green section, even though the velocity is still positive, you are slowing down. So you're still going to the right, but you're slowing down. In this little section, the velocity now is negative, so you're moving to the left, but you are speeding up. In this little section, you're still going to the left, but now you're slowing down. That means that in between, since you were slowing down and then speeding up, right here at that one moment must be the fastest you were going in this time block. And in fact, in terms of absolute value, that's the point that's farthest away from the t-axis. So that has to be actually corresponding to the fastest speed if you take the absolute value of the velocity at that time. Also notice there's a time where you go from the right to the left. At that time, you must have changed direction. So now you have a basic introduction to velocity. We can move right to acceleration as it's just a simple extension of what you've already seen. The acceleration is just given by the rate of change of velocity with respect to time. So that would be the derivative of the velocity with respect to time. But the velocity is the derivative of position. So acceleration is just the second derivative of position with regards to time. And it's the first derivative of velocity in terms of time. Now, velocity has to do with the motion of the object left and right. All acceleration does is it measures the change in the velocity, and it also indirectly measures the change in the speed. Don't think acceleration is strictly changing speed, because it's not, because acceleration can be positive or negative. It also, later on, it will also measure a change in direction. Just right now on number line, we have only two directions, left and right, so there's literally not much to do there. So let's revisit the motion of a particle moving on a line and the graph of the velocity function I gave before. Let's go look at this graph and determine what we can figure out about the acceleration of the object. Well, if you look at this piece, remember the velocity wasn't changing and acceleration is the rate of change of velocity. So then the acceleration this whole time is actually 0. In this next time interval, this piece, the acceleration is actually always negative. That's because the velocity is always decreasing. Now you can see it probably a little bit better if you remember that the derivative, and that's the acceleration, it's the derivative velocity, has another interpretation. It's the slope of the tangent line. Look at every single point in this portion of the graph and look at its tangent line. See how the slope is negative? For the same reason, if you look at the next little section, the acceleration is actually always positive. And in between, there's one place where it's not positive, it's not negative, it must be zero. So there's one time right there where the acceleration must have been zero. In the next time interval, this whole time, the acceleration was also zero because the speed was constant that entire time. All right, let's look at a very, very simple numerical example. Let's suppose you have an object that's in free fall. It travels then 4.9 times t squared meters just after the first t seconds, where distance is measured downwards from its starting point. So the positive direction is down. How many meters does it fall in the first 3 seconds? Well, that's just found by going and evaluating the s function at 3. So that would be 4.9 times 3 squared, and that would then be 44.1 meters. That's how far it falls. Now I want to know its velocity and its acceleration. Well, velocity is just the derivative of position with regards to time, and that would then be 9.8 times t. Acceleration is the derivative of velocity with regards to time, and that would just be 9.8. So this means that if I'm only looking in forward time, so where t is bigger than 0, the velocity is actually always positive, which makes people upset because when we think of objects that are falling, you think negative velocity. But remember, I'm measuring everything from where it fell. So downwards is positive. So you should expect a positive acceleration, and you should expect a positive velocity over this entire time period. So let's do a projectile problem. Let's suppose a rabbit, this will be a super rabbit you'll see, hearing a gunshot will jump straight into the air. Its position relative to the ground is given by this formula. I want to know, what is its maximum height during its flight? Well, think of it this way. If the velocity is positive at that time, well, that means then by increasing time, you would increase the object's height. Well, so then it can't have positive velocity. If at the time you're at a maximum height and the velocity was negative, then by decreasing the time, you would then increase the height. So then there's only one possibility left, that the velocity is 0 or it doesn't exist. But the velocity as a function is just the derivative of the position in time, and that's 64 minus 32t, and that always exists. So the only time when we could get a maximum height is when the velocity was 0. So I'll just solve that the velocity is 0 for t. That gives me 64 minus 32t would then equal 0. That means that t would then have to be just 2. So I need to know then, what's that height? So I need to know what's the position after 2 seconds. So that's 64 times 2 minus 16 times 2 squared. And I'm going to cheat like crazy here for a minute. This is actually a 64 times 2 minus a 64. You can think of it as times 1 if you want. So that would then be 2 64s minus 1 64. That's just 64. And that would be then in feet. And that's the maximum height of this rabbit when it jumps in the air. As I said, it's a super rabbit. So let's revisit that super rabbit. And this time, I'm interested in finding out what's its velocity when it is 48 feet in the air and still on the way up. So first, in order to do this, I need to know how to find the velocity function. So I know that the velocity as a function of time, we already computed it. It was 64 minus 32t. But I need to know when to evaluate that to get that velocity. Now I want to know then what's that velocity when it was 48 feet in the air. So I'll have to solve when is its position exactly 48. And I'll have to solve that for t. So writing down that equation, you would get 64t minus 16t squared is equal to 48. If you then go and just divide everything by 16 to get rid of some of these numbers, you would then have 4t minus t squared is equal to 3. By bringing everything to one side, let's say the right, and then just organizing the equation, you would get t squared minus 4t plus 3 is 0. So that means t minus 1 times t minus 3 is 0. So there are 2 times that I have to worry about. But they said on the way up. So I need to evaluate the velocity at both these times. So the velocity at time 1 would then be 64 minus 32 times 1. That would be 32. And in units, that would be feet per second. The velocity at time 3 would then be 3 seconds. That'd be 64 minus 32 times 3. And that's a negative 32 feet per second. So they want to know the speed on the way up. This is when the velocity is positive. That's when we're going up. So the speed would then have to be the absolute value of that velocity, which happens to be 32 feet per second. Notice at time 3 seconds that you're going the same speed also. You're just going down. So let's get beyond these motion problems and get back to just a general rate of change problem. So the typical male surface area can be modeled by this formula, where W and H are their weight in kilograms and height in centimeters. Now this is just an approximation. Don't think too deeply on it. Find the rate of change of the surface area with respect to the weight for a male whose height is 180 centimeters. So first, I need a way to get the surface area in terms of the weight only. So let's go ahead and simplify this formula. The surface area then would be given by 1 over 60 times the square root of the weight, which is what I don't know, times the height, which is I do, 180. That then is the square root of 180 over 60 times the square root of W, which I can write as W to the 1/2. But the square root of 180 is divisible by 36. So then that would then be the square root of 36, 6, times the square root of what's left over, 5, all over 60, times W to the 1/2 power. So that then is the square root of 5 over 10 times W to the 1/2 power. Okay, great. So now that I have that, the next step then is how do I know a derivative is needed? Well, right here it says rate of change. That's a humongous hint. And then to figure out what the derivative should be, it's the derivative of this variable in terms of that one. It says surface area and with respect to. So think of respect to as per the weight. So I have a change in surface area per a change in weight. So that's the derivative I gotta crank out. So that's fairly easy. It's just applying the derivative operator to the square root of 5 over 10 times W to the 1/2 power. And that would then be the square root of 5 over 20. Don't forget coefficient times power. Keep the base. And then reduce the power by 1. Rewriting it one last time, that's the square root of 5 all over 20 times. If you take the power and put it down in the denominator, so you have W to the 1/2 power, write it instead as the square root of W. And that's it. That gives you the rate of change of the surface area with respect to weight for this male of height 180 centimeters. And that gives you a basic introduction to derivatives as a rate of change, and also investigating a little bit more closely position, velocity, and acceleration.